Ladies and gentlemen, it's my great pleasure to introduce the next speaker, which is Albert Laszlo Barabasi. Laszlo is the Distinguished Professor at Northeastern University, where he directs the Center for Complex Network Research. He also holds positions in the departments of biology, of chemistry, of computer science, and also, as you can see, positions at the Harvard Medical School. He's perhaps best known for his work in complex networks, and his work is actually the one that discovered the idea of scale-free networks, which have been applied so widely in many areas. We've seen that the social networks are also scale-free, that the internet is scale-free, so really it's the answer to everything. He's also done significant work in the field of systems biology, where he's taken the ideas that from networks and use these concepts to describe the way that biological components interact. Both of these areas of research have led to a very, very impressive publication record, and you will see his work regularly featured in both Science and in Nature, sometimes appearing on the cover. So there are many kind of numbers, statistics that I could tell you about his career and impress you completely. But the two numbers that I would like to tell you, and I think relevant to today's talk, are to do with the Erdős number and the Bacon number. So if any of you know what that means, that's fine. You'll also be interested to know that Laszlo has a Bacon number of 1, which is quite impressive, and an Erdős number of 4. If you don't know what this means, then luckily we have a world expert to tell you exactly what it means. And with that, I'd like to introduce Laszlo Barabasi.
Thanks, Michael, and I will not explain actually what it means, but we'll talk about other things pertaining to networks, and thanks for the opportunity being there. I really share fully the basic idea behind this conference. I think this century will not be the century of complexity. I think it is the century of complexity. I think the train is really running with 5 speed, and I'm glad that you guys are part of it, and so in a way, and Santa Fe has really been the, kind of at the forefront, doing it at a time when this was not popular. Now the field has grown up, and we have all benefited, including myself, from the pioneering work that Santa Fe and its sister institutions have done. So what I want to do today is indeed talk about networks, and I hopefully will convince you by the end of the day that networks play a very major role of understanding complex systems, and they're part of the reason why the train is running so fast momentarily. And let's just get it out, a couple of examples of networks just to fix our language. So when I talk about networks, I talk about objects like the internet, where routers are connected to each other by a physical cable, so this is a physical network. But we can talk about an organization, like a company, where individuals are connected to the people whom they work with, whom they communicate with on a daily basis. And we'll come back to that and talk about some aspects of that. We can talk about, at large scale, about Facebook. This is actually a famous map that came out a few years ago. Oh, by the way, can we get the lights a bit lower so that it's a bit strong and some of the videos will not work out too well, if there's a way. So, so this actually shows how the user base of Facebook are connected to each other, through the various friendship links that they volunteer to the site. But one of the things that these examples have in common is that they are very large and complicated networks, and in order to really talk about them in a quantitative manner, then we really need to develop language to do so. And the language for that was really developed, some of the roots of the language go back to the 1960s and the work of 2 Hungarian mathematicians, Paul Erdős and Alfred Rényi, who down the line made a very simple hypothesis. They said, all these networks that are around us, and in their first paper they used the biological and transport networks as examples, they said, well, they're too complicated for us to comprehend, but they look random. So let's go ahead and build a model that acknowledges that randomness. And they said, well, at the mathematical level, networks are very simple objects. There are nodes connected by links, so let's build the simplest model that can achieve that, put a number of nodes, take every pair, throw a dice. If you get a 6, you connect them. If you don't get a 6, you don't connect them. So through this process, you end up with what we call a random network. And how the random network model looks like depends on this parameter P, which tells you what's the probability of two nodes being connected. And this is how a network like that would evolve. So at time 0, you start out where no nodes are connected, so P is exactly 0, everything is isolated, and then you crank up P a bit. And by adding a small P, you will have pairs of nodes who end up being connected, and you can go ahead and increase slightly more the P, gradually increasing it towards larger and larger values. The consequence is that some of these paths, some of these pairs that got connected earlier will join each other. They will start forming little trees and pathways. And when this P gets large enough, these trees join each other as well. And then suddenly, an object that looks like a network that we recognize as a network will emerge in the system. And what Erdős and Rényi have done is that they have shown, using the language of physics today, that the emergence of this, what we call a giant component, is not a gradual process, but it's a sudden one. It emerges through what we call a phase transition now. So for a range of p-values, you don't have a giant component, you really don't have a network. And then once you reach the critical point, suddenly the network emerges. It's still tiny, and as you increase further, then this tiny network, tiny cluster will start absorbing all the other nodes, and eventually becomes, all the nodes become part of the big cluster. So that was the picture that Erdős and Rényi has really given us. And one of the most important characteristics of this network is what we call the degree distribution, which is simply the probability that a node will have exactly k links. And in an Erdős and Rényi network, the degree distribution follows simply a Poisson distribution. And the meaning of that is that the most nodes have approximately the same degree, which is around the average degree where the distribution has its peak, and it's exponentially rare to find very connected or not so connected nodes in the network. So if this would be a model of society where people meet randomly and become friends with each other, in Erdős and Rényi's world, most of us would have approximately the same number of friends. There would be no hugely popular individuals, and there would nobody really left behind. So it would be a society of the averages. And naturally, the question comes is that do we really believe that real networks are random like that? And to answer that in the quantitative terms, we need to get examples of real networks that we can study and confront with the predictions of the Erdős and Rényi model. And we started thinking about that. We actually chose to study the World Wide Web. Why the World Wide Web? Well, the name says it's a network. It's a very large network. It's over 1 trillion documents these days, where the nodes are the documents and the links are the URLs that connect to the different web pages together. And the reason why we focus on the World Wide Web, because this network is public. You can map it out. You can just start from a web page and click and go to the next pages that the links are over there. And of course, by hand doing that, it's a rather boring process. So you can build a robot that does the trick for you. And at the end of the day, it returns you a map like that, where the nodes are web pages and links tell you what are the web pages that you can reach with one click from that page. Our expectation was that because each web page reflects the personal interest of different individuals, and given the diversity of the interests we have, this network should be more or less random. Because I really don't know whether you're going to connect to sumo wrestling or network science or Picasso's paintings. And given that, if the network would be random, we would expect to have a power like a Poisson degree distribution. Yet the data indicated something completely different. It showed us that there's a power law tail in the degree distribution. So this is the probability that the web page will have k links going in or out. And k versus k on a log-log scale, and the fact that these data points more or less line up along a straight line indicates that the probability that a web page has k links goes like k to the minus gamma. This gamma exponent here, or what's called a degree exponent, is about 2 in this context. So fine. What we found is that the World Wide Web happens to have this property, but does it really mean anything? And to illustrate the meaning of that, it's best to compare the random network to this power law network. And the random network visually is a bit like the highway system of US or Asia, as a matter of fact, where the nodes are the cities and the links are the highways or the major roads connecting them. And it's a relatively uniform network in the sense that most cities have 2 or 3 highways connecting them to the rest of the network. You don't find cities with hundreds of highways, and you don't find any on the mainland US, let's say, that wouldn't have at least 1 or 2 highways connecting them to the main system. So this would be something along those lines, yet the power law distribution would give you something that looks much more like the airline system of US, where you have many, many small airports and a few major hubs that hold them together. So and this is indeed what the power law tells us, because we have a log scale here, it tells us the vast majority of the nodes are in the small degree territory. They are the small airports, but you have a few very highly connected nodes or hubs that really hold the whole network together. And these networks today are called scale-free networks, and the scale-free term really refers to the fact that in the random network, you can pick the average node and say this is characteristic to the system, because most nodes have approximately the same degree. In a scale-free network, the average is not characteristic because the second moment of this distribution is typically diverging, goes to infinity. So for example, the meaning of the average in the case of the World Wide Web is that a typical web page on the World Wide Web has degree 7 plus minus infinity. So when you say degree 7, it's not meaningful because the spread is so wide. So there is no intrinsic scale in the system. All the different degrees could actually be possible in the system. So, all right, so what we find is the World Wide Web happens to be this animal that has a power law degree distribution, maybe the airline system, but are there other systems as well that would follow that? And of course, the reason why this thing became somewhat more exciting is because there are some other systems who follow the same property. This is a map of the internet. This is not the World Wide Web. This is a physical network where the routers are connected by physical cables. And you can see that, yet despite the fact that it's a very different hardware network, there's a few major hubs holding together many, many peripheral nodes. So different structure, different purpose, different technology, yet they converge to the same technology. Now, I'm sure many of you are fully aware of the fact that today is actually the Oscar night. So let's talk about Hollywood, therefore. So I guess the Oscars just been finished about an hour ago, or an hour and a half ago. And there's actually a network behind Hollywood where the nodes are actors and the links are, two actors are connected if they played in the same movie together. So for example, Tom Cruise and Nicole Kidman used to play together. In the past, they did so. Therefore, there are several movies that link them together. So if you rebuild this network behind Hollywood from 1890 till today, all the movies played and all the actors, how they're connected to other networks, you would find that the vast majority of the actors have a few links only, and a few have really hundreds and thousands. And of course, these in the small degree region are the individuals, the actors whose name you never know because you walk out of the movie theater before their name scrolls down the screen. And there are, of course, the hubs that hold the whole network together, which are the big stars that we all pay attention to. Now, one example one of the common things between these systems that I showed you so far, World Wide Web, Internet, Airline Network, Hollywood, is that there are man-made systems. So, which raises a fundamental question, is the scale-free property, is the emergence of the hub, is something that we do to these systems? Is this somehow a consequence of human actions? So to answer that, it's really good to look at systems that we did not consciously create, like the networks within our cells. So on the left-hand side, you see the metabolic network. That's a network of reactions. Most of you have had lunch. Therefore, this network is terribly active. It's breaking down the food molecules that you have eaten, the rice and the noodles, into the components that your cells can recognize, because the cell doesn't really know noodle from rice. It can just know ATP and other simple molecules. So that's the reaction network on the left. On the right-hand side, you see the protein interaction network, where proteins interact with each other. If there's a link between them, it means that they bind to each other. And look at the right-hand side, it's even more visible there. So there are many peripheral nodes with one or two links, and there are a few major hubs that hold the whole network together, indicating that, and actually there's quite a bit of evidence that these networks within our cells have this scale-free property. Which kind of, if you think about it, it's pretty amazing, because the World Wide Web has a history of 20 years. Like last year we celebrated the 20-year anniversary of Tim Berners-Lee's first web page. The internet has a 50-year history, or you name it, airline system, I don't know, maybe 100 or 50 years. And yet this has 4 billion years history. And then how is it possible that something over 4 billion years have really converged to the same structure as the World Wide Web? And not only that, so here I'm just going to show you a list of networks that people have documented as being scale-free. For some of these, the evidence is very strong. For others, are somewhat shaky. But nevertheless, you can see the degree of variations between different type of networks. Purpose, size, nature of the network is vastly different, yet they all kind of converge to the same scale-free architecture, which raises a fundamental question: why? How is it possible? How is it possible that the cell and the World Wide Web really chose to converge to the same architecture? And to answer that, we have to go back to Erdős-Serényi and ask ourselves, what has gone wrong with their model? Why are they not predicting the hubs? What's missing from there? And if we do that, we realize that the Erdős-Serényi model has two hidden assumptions. The first is the philosophy of how it models the system. Its philosophy is first start with a fixed number of nodes and later connect them. That is, your role as a modeler is to place the links in a clever way to mimic the system's behavior. Yet in real networks, the number of nodes is not fixed. The links and the nodes come together. Indeed, think about the World Wide Web. You know, we have more than 1 trillion web pages. How do we have more than 1 trillion? Well, they came one page at a time. Everybody was creating their own web page. So if you really want to model the World Wide Web, you can't really start out with drawing 1 billion dots and then connecting them later, but rather you should really start out from a small nucleus and add the new web pages to gather the links, mimicking the way the network was built in the first place. The second assumption in the Erdős-Serényi model is that, you know, how do we choose where will the new node connect? And it tells us you can choose randomly. And I would argue that's not correct again. But new nodes prefer to link to highly connected nodes. And the web, again, is an easy place to understand this mechanism. You know, there are more than 1 trillion pages out there. Well, how many do you know personally? A few hundred, maybe? Which are the pages that we all know? It's like Google and Yahoo. And so there typically our knowledge is biased towards the more connected pages. The more links it has, the more likely we'll be familiar with that. And therefore, the more likely that we'll connect to it, because we connect only to things that we know. So if you want to put this is what we call preferential attachment, and it's a stochastic rule telling me that the probability to connect to a web page or to a node is proportional to the number of links it has. Anyway, you know, it tells us that I can connect to this guy or to that guy, but I'm twice as likely to connect to that guy than that one because this has 4 links and this has only 2. And if you kind of now grow a network with these rules, you will see that hubs will naturally emerge. And the reason for that is a rich gets richer mechanism. That is, if a node has many more links than the other one, the new nodes who come to the system are much more likely to find the big guy than the small guy, and therefore the big guy will grow faster than the small guy, and hubs will naturally emerge. So if you run this system, you know, to many, many nodes, you will find that the power law degrees, the degrees follow a power law with an exponent -3. But there is one problem in this model, because it tells us really what we call in business world the first mover advantage. It tells us that the biggest hubs will always be the earliest nodes, because it tells us that each node will increase its degree as t to the 1/2, and therefore the biggest node will be the one who had the most time to acquire a link, that is the first to arrive into the system. So it would look like that, you know. So nodes come at different time, and they all starting following the same curve, but at any moment, the first guy will always stay the first. And the problem with this is that obviously we wish this would not be the case. You know, we wish that the later node could actually have a chance to overcome the earlier nodes. And we have examples of that. And Google is a good example. Google was a relatively late comer to the World Wide Web. You know, it was started in 1997, I think, like 6 years after the web was created. And then it became very soon the biggest hub. And now Facebook came around a few years later, and now that's the biggest hub. So clearly in real networks, there are mechanisms by which a node can come late and overcome the earlier nodes. We need to somehow incorporate that one into this model. And to do so, we need to add one more property of the nodes, which is really goes beyond their degree, which I would call fitness. Fitness is really an intrinsic property of the node and tells us how likely the nodes will acquire links. So, you know, fitness is, you know, will you actually want to ever call that person who you met yesterday, or you want to toss away his or her card? Fitness is the likelihood that once you go to a certain web page, will you ever want to go back again? Or will you ever want to link to it, or you will just forget it right away? And so each node has an intrinsic fitness, and the best way to model that is to say, I don't know what each node's fitness is, so I assign a random number as their intrinsic fitness is, and therefore I need to modify the preferential attachment to say the probability that I connect to a node is the product of the fitness and the degree. And the reason for that is because the degree is still there because that tells me the visibility of the node, and the fitness tells me once I found that node, will I or will I not connect to it? So that's why you have both of them. And if you do that, you will find that each node will increase its degree as time to a certain exponent beta that is proportional to the fitness, which means that now different nodes with different fitnesses will grow at different rate. So it's possible in this environment that a node will come late, has a higher fitness, and with time will actually overcome the earlier nodes. But the model has actually some drawbacks, and one of the drawbacks of the model, actually some of the interesting predictions, not as much drawback, is kind of along these lines. So it depends on where you choose your fitness distribution, what the behavior of the system will be. For most well-behaving fitness distributions, you will just simply develop a scale-free network. So here the numbers tell you the order in which the nodes arrived, and the color tell you their fitness. And what you can see is that the biggest node will not be the earliest node, but rather the darker color node who came relatively late but had a higher fitness. And in most situations, despite of competition based on the fitness, the network will actually end up being scale-free. In some cases, will not be scale-free. And this is an example of a system where one node will come in with such a high fitness that it will grab actually all the other links. In mathematical terms, what we see is a Bose-Einstein condensation, and the way this actually plays out is that while in a scale-free network, as the network grows, the biggest hub grows as well, its market share, that is the fraction of the links the biggest node has compared to all the links, goes down with time. That the bigger the system, the smaller is the market share of the biggest node. In this environment, the biggest node has a constant market share, and therefore, as a system is getting bigger, so does the bigger one. And visually, the way you would imagine is to think about the market share of Microsoft. Despite the fact that over decades, the number of users has really exploded exponentially of the different operating systems, the market share of Microsoft stayed about 85%, for a very, very long time. And that would be a signature of a Bose-Einstein condensation. If the network would be scale-free, Microsoft could be still the biggest operating system, but its market share should gradually degrade because the biggest hub's market share will go down in a predictable way. So let me change gears and talk about another aspect of these networks, which is to say, why does it really matter that we have hubs in the system? Do the scale-free property affect the properties of the system or not? And one of the things we learned in the last few years that it does affect, and there have been some really wonderful results on how, for example, spreading processes are affected by viruses. Alessandro Vespignani has done, and many others, some great work on that. What I'll talk today is really the issue of robustness and how that affected by the structure of the network. Well, what is robustness? Well, robustness is an ability of a system to maintain its basic functions even when some of their components may be failing momentarily. And if you think about the cell, as I'm talking to you, there are probably millions of errors in my cells, and yes, I don't notice it. And at any moment on the internet, there are measurements showing that hundreds of routers are not functional. They could be fixed in 10 minutes or an hour or maybe in a day. But despite that, the internet as a whole continues to be functional. So how would you model that? And the best way to model that is to say, well, what happens if I knock out some nodes from the network like that? Well, what could happen is that if the right node gets knocked out, then the network could break into pieces. And this is what I'm illustrating over here. The network is really broken into different clusters. But the fundamental question is really, what happens if you take a large network and you randomly start knocking nodes out? And the answer to that really comes from percolation theory. This is what you would see what we call an inverse percolation problem. You start from, and if you would have a regular network like a square lattice, or you would have a random network like the Erdős-Rényi, then the answer is very well understood and very precise. The answer is, if you remove randomly a few nodes, it doesn't really matter. You're shrinking the network a bit. But as you remove more and more nodes, you will undergo an inverse percolation transition. And that is at a certain critical density of nodes removed, the network will break into tiny pieces and will fall apart. And each network has its own calculable critical point that depends on really only one parameter, the degree distribution of the network. Once you know degree distribution, you can calculate the critical point of the network. So the question is, what happens if we do that for a scale-free network? For a random network, we know that it's inevitable the network will fall apart once the critical point is hit. So let me do that. So I'm starting from the network that I showed you earlier, and I'm going to start removing randomly nodes. And what is puzzling about this picture that you may notice is the network doesn't really want to break apart. And as you're removing more and more nodes, you realize that the network is shrinking, but it's really hard to break it. And the reason for that is the existence of the hubs. We have a few hubs and many, many small nodes. If you choose the nodes randomly who to knock out, you are much more likely going to knock out a small node because there are many of them. Your chance of hitting a big hub is very, very close to zero. So therefore, you will shrink the network, but you will not destroy it. And indeed, now it's actually been proven exactly by Béla Bolobás and first shown by Shlomo Havlin and collaborators that a scale-free network has its critical point equal to 1. What does it mean? You can remove 99% of the nodes. If the network was large enough to start with, the remaining 1% of the nodes are still hanging together and talking to each other. So random failures don't destroy scale-free networks. Obviously, the network is big enough. In a small network, you could do that, but in a large network, the chance of destroying it by random failures is very, very low. But of course, there's a price you pay for that. What if you don't remove the nodes randomly? What if you start with the biggest hub, and the next biggest hub, and the next biggest hub, which is what I'm doing here. I'm going on attack mode. I know the structure of the network, and I'm removing the hubs one after the other. And you can see that in no time, the network is broken into tiny pieces. And let's compare these two pictures. We started from the same network. On the left-hand side, I removed randomly 16 nodes. On the right-hand side, I removed in a targeted way 9 nodes. And you can see that on the left-hand side, they're still hanging together. On the right-hand side, it's broken into tiny pieces. And that's what we call the Achilles heel of scale-free networks. They're very robust to random failures, but they're very fragile to attacks. And this duality could be good or bad news depending on where you are looking from. If you are an internet researcher, so you care about the integrity of the internet, the robustness is good news. It tells us random failures will not corrupt the structure of the network. But the bad news, of course, is that if somebody has a detailed knowledge of the internet infrastructure, by knocking out the right routers could actually do quite a bit of topological damage. If you are a biologist, then you say, this is both good news, because on one hand, it tells me that random failures will really not kill cells, and that's kind of one of the sources of robustness in our living systems. But it also tells us, but by knowing the hubs, I could probably design drugs through which actually I could kill cells that may not be appropriate, or I may not want in the system. So depending on where you come from, this could be good news or bad news, and you can exploit it in different ways. At this stage, I would like to kind of switch gears, sorry. This is making noise. And I'd like to talk about the second part of this lecture, which is about, how do we think about controlling networks. And I think I ended up getting out of here we are. And to understand the motivation for that, at the end, we have to realize that whether it's biological systems or non-biological, or complex systems or non-complex systems, understanding a system really means that we have to quantify it. We're able to quantify the system, as we're able to measure it. We can predict some of its behavior, which really implies that we can draw mathematical laws and regularities from the system that gives predictive power to us. And the ultimate proof of our ability to actually understand the system is really, can we control it? So, but of course, the word control has many, many different meanings. We heard about the 380, and some of the issues about controlling that. So you can think about how you control an airplane. That is actually a word where control is used, particularly in the case of drones, which are controlled remotely. But when it comes to control, you can think about personal control, controlling your emotions, controlling your feelings, self-control, and so on. Or somebody like me who actually grew up in Eastern Europe, the word control has many other meanings, social control, dictatorships, and so on, that we really certainly don't want to experience in a way or the other. So the challenge is really for us is that how do we formulate the concept of control in the context of complex systems? And to do so, we actually chose to go to control theory, a well-developed field of engineering, and borrow their sense of control, because that particular area of engineering has been really thinking for many decades about how you control a system. And they have a very simple answer to the control problem. They say a system is controllable if it can be driven from any initial state to any desired final state. Now, this may sound actually rather cryptic, so let's try to translate it to what this really means for us. What do we mean by control in this context? And the best way to understand that is to think about a car. A typical car has about 5,000 components. Yet, when we drive a car, we never think about those 5,000 components. We rather think about three. We think about the gas pedal, the brake, and the steering wheel, and from there you can actually control the full car. Every time you push on your gas pedal, you're turning on thousands of components in your car. You're making the car actually, many components to work simultaneously to do certain things together. Yet from the control perspective, you can make the car to go from anywhere to anywhere through these three components. And if you can, then you got a major problem with your car. So now, of course, the reason why you can do that is because the car and many other engineering systems have been designed to be controllable from very few components, you know, like switches and gas pedals and so on. But let me ask you the following question. What if somebody gives you the inverse problem? That they give you the wiring diagram, the mechanical and electrical wiring diagram of a car, and let's assume that you know nothing about cars, like I don't know much about cars either. And the question is, could you figure out from this wiring diagram what are the control points from which you can control the whole car? That where is the steering wheel, where is the gas pedal, and where is where is your brake? And this may be quite a bit of waste of time at the first thought because you say, hey, why would I do that? They already know that it's been designed like that. But if you think about it, this is the type of question that biologists do day by day. They try to figure out how is a cell controlled, or how could you control a cell to actually solve some diseases, you cure diseases, or how does cancer emerge in the first place? What are the components in the cell that really control the other components? And this is the type of question that, if you are in charge of a new organization, you need to figure out, how do you come into a new organization and make them follow your vision? How do you control the system? Even though the word control here may seem a bit harsh in a social environment. So in lots of different areas, we actually, in the scientific world, we face the same problem. We have approximations of the wiring diagram, perhaps not complete. How do we understand how to control that particular system? And that's a problem that we've been working in the last 2 years, and some product of this work came out last year in Nature. And let me kind of take you through how we approach this problem. So in order to talk about control, you need to have the dynamics of the system. So you have to define a dynamical system, and that's what we do over here. So we say, in the simple case, we have a system made of several components. In this case, I'm showing only 4 of them. And in each component, there's some state variable, the traffic on that node, the status of that node, whether it's on and off, or whatever the proper state variable of that node is. And that's the vector x. So vector x tells me what is the current state in the system, and that is time dependent, of course, because that changes. The matrix A really tells me who is influencing whom in the system, which is really the wiring diagram. That's where I put my network in, who is influencing whom, who is talking to whom in the system. And the control problem can be, for now, we assume that we have a linear dynamics on the system. So the state variable depends on the previous state variables. And the control problem is defined through these last 2 terms, which is we need to define a couple of controllers. These are the nodes through which we have direct access. This is the steering wheel and the brake of the car, for example. And by controlling, I mean that I can actually vary the state of those that I'm controlling. So I'm able to inject a time-dependent signal just like I'm turning in function of the time the steering wheel. So the full problem really is defined like that. I have a number of controllers. I have a number of nodes that need to be controlled. And the question that I need to ask, can I really control the full system by controlling these 2 nodes? Now, obviously, I can control any system if I control every single node. But that's not practical in most systems, and it's not possible in other systems. So the question is, what is the minimum number of nodes I need to control such that the rest of the system will follow through? And that answer has been answered, that question has been answered by Rudolf Kalman in 1963. He's a mathematician and control theorist who currently actually lives in Switzerland. And what he said is that you can build what we call a controllability matrix, which is really just the time evolution of the system across several steps. And if this matrix has rank n, then the system is fully controllable from those control points that you have chosen. If the rank of this matrix is smaller than n, then the system is not controllable. That is, there will be some variables that you cannot control to the which you are controlling. So let me illustrate that. So this would be a system that I can easily control from the top down, because if I control this guy and that controls that and that controls that, therefore by changing the state of x1 to this u1 signal, I can make the system to go from anywhere to anywhere. On the same token, this looks to be a system that I can fully control as well, but I can't, actually. The Kalman condition will tell me that my controllability condition will fail in this case. And the reason it will fail is that if I change the state of x1, I cannot make x2 and x3 to go in different directions. I can make them go together up or go together down, but not in a differentiated way. So I don't have full control over the system. Now you will say, how do I have it here? And the reason I have it here is because I'm inserting a time-dependent signal, and there are always time delays along the links. So at the end, I can make this guy go anywhere I want by sending the proper time-dependent signal early on. Now, can I fix this system? Yes, I can. I need one more controller to do that. So I need to control 2 of these nodes, and then that particular system becomes controllable. So the reason I'm showing these examples, A, to develop some intuition, and B, to understand that control is not simply just looking at who are the more connected nodes, but there are lots of detailed caveats of how we think about control. But let me tell you where the problem is when we apply control theory to networks. At first sight, it looks like the problem is solved. We have the Kalman condition, and that tells me whether this or that system is controllable. It tells me that this is yes, this is no, and this is yes. So it looks like there's nothing to be solved here. But in reality, we have major problems here. And the first problem is that in order to apply the Kalman condition, you need to know the weights, because you need to know the full matrix. And in most systems, the weights are either not available or they're time dependent. So you can't really apply a static picture to that and get the answer to that, because it will always change from time to time. This is the problem that is the easiest to solve, because it turns out that we can adopt a framework which is called structural control theory, where we can ignore the weights, and the answer what we get will be precise except the 0 measure level error that we can get. That is that most of the time we'll be correct about our predictions, but there will be some pathological cases of the weights when the conditions will not pan out, but that will really have 0 measure, so we don't have to worry about that. So this is the easiest problem to solve. The bigger problem is this one. The Kalman condition does not tell us who are the control nodes. It tells us that once you made the guess, whether that's a control configuration or not. So the truth is that if you want to figure out who I control the system, first you have to try one by one each node. And if none of them alone can control the system, then you have to try each pair. And if that's not enough, then you have to try each trio and so on. So before you notice, you are actually checking out 2 to the n different conditions. And that will tell you whether before you find your control configuration. So that's, for a network of few components where typically control theory is applied, is not a problem. For a network with thousands of nodes, it's impossible to perform that calculation. Not only that's impossible, but even Kalman's rank condition for large networks is impossible to decide, because many of the algorithms that help us decide whether a matrix has rank n are actually unstable for large n. So you can't really apply to, let's say, like a million by million matrix, this particular condition. So the bottom line is that we don't have a criteria by which we find the control nodes. We have to test each pair, each trio, and so on, until we run across one that will achieve that. So this is the problem that we really set out to solve. How do you find the control nodes? So what I'm going to do is switch gears and talk about the problem that apparently has nothing to do with control theory, but it's a fundamental graph theory problem, and that's the so-called matching problem. So matching is really, it's almost like a game. So let's start out from a network, and let's find out, let's color some of the links red in this particular context. And the criteria for coloring them red is that I want to make sure that none of the red nodes end in the same node. None of the red links end in the same node. And of course, there are many different ways of doing that. And the challenge is find the maximum number of red bonds in the system such that none of the red bonds touch each other. And that's also called the matching problem, and this has actually many practical applications. For example, in US, the medical school admissions are decided using a matching algorithm, where students tell, I'm interested in this ranked order in these universities. The university said, I'm interested in this list of students, and then the matching algorithm is the one who tries to find the best match between the two that the most satisfies everybody's needs as much as possible. Now, so that's how matching looks actually in an undirected network. What I would like to talk today is about directed networks. And the idea is the same. I'm trying to find a set of edges without a common heads or trails. So they can have the common head and trail, but they should not have two common heads or two common trails. So for example, in this case, the maximum matchings look like that. And the best is, here we actually have 3 nodes because none of them end up or come from the same node. And here, there's only one link that can be matched. The rest of them, any other link you want to play red, will be coming out from the same node, so you cannot do that. So why do we care about this problem? The reason why we care about the maximum matching in networks is because we were able to prove that the control problem can be exactly mapped into this matching problem in the following way. The driver nodes are what we call unmatched nodes. So let's see what is the language of unmatched. A node is matched if a red bond is pointing at them, and it's unmatched if there is no red point pointing at them. And what this minimum input theorem that we proved actually tells us is that every node to which in the matching there is no red link pointing to them needs to be controlled. So if you want to control this network, these 3 nodes have to be controlled, or these 3 nodes have to be controlled, or these 3 nodes have to be controlled. In this particular case, any node can be controlled, and it will actually control the full system. So that's an anomaly. In this case, this is the node you need to control, and that will control the rest of the system. So what is it we achieved here? Essentially what we say, if you have a network, now you can go ahead and find the maximum matching. So this is one example of maximum matching in the system. You can see that there is no other purple link you can place in the system such that they don't start from the same node or write to the same node. And then you control the non-matched nodes, and then you get a complete control configuration. And there is many different ways you can achieve that. Here are 4 different ways. What is common between them is that the number of control nodes is the same, but the control configuration is slightly different from one system to the other one. And now, of course, you may ask, what is it we achieved here? Because at the end, we took in one problem, which was NP-complete. We had to try 2 to the n configurations, and we mapped into another problem, which is just as difficult. Because if you think about taking a large network and finding the maximum matching, could be quite a time-consuming exercise by itself. But the reason why this is interesting is because finding the maximum matching is not NP-complete. We know it's not. And the reason it's not is because while in principle the brute force search will require 2 to the n different trials again, in reality there is a well-known polynomial algorithm, the whole so-called Hopcroft-Kraft algorithm, and the very existence of that algorithm shows us that this is not NP-complete. Therefore, we can actually decide the matching in a polynomial time. And the consequence of that is that now we have a polynomial algorithm that allows us to take a very large network, find the maximum matching or not, and then from there identify what are the control nodes. So we have now the machinery, the numerical machinery in our hands. You give us the network, we can figure out who are the control nodes, just from the network topology, ignoring all the dynamical rules in the system. And what we did is that we applied this tool to a bunch of real networks. So these are the common thing between these type of networks is that they're all directed networks. And I need to warn you that most of these networks are not involved in control, so it's not particularly meaningful to apply control theory in them, because if you think about the World Wide Web, what is being controlled there? There's not much being controlled there. But we wanted to apply this thing just to have a sense of what is the diversity of the answers we get. So what you see here on the horizontal axis, different type of networks. On the vertical axis is ND, which is the fraction of the nodes that are control nodes in the system. So if it's 0, it means that a very few nodes can control the full system. If it's close to 1, it means that you need to control each node individually such that you achieve complete control over the full system. Now, if you look at this map, you realize that the first thing is there is no systematic order that you can see on this map. Each network has a typically different number of control nodes you see. But there are actually two caveats here that were surprising for us. As a group, regulatory network would actually turn out to have a highest ND. Now, this was very surprising to us because the regulatory network is the network in the cell that is really responsible for controlling the cell's behavior and the state of the system. And so we thought this should be easy to control. And if it's easy to control, it means a few control nodes could actually achieve full control. Yet, the answer was the opposite. It turned out that among the many systems we looked at, the highest number of control nodes were required in this regulatory network. On the other extreme, we thought social systems should be the hardest to control because none of us wants to be controlled. So we all have individuality, way to think about, and so on. Yet what we find is that some of the lowest control nodes is really in interorganizational or in social networks. So in a way or the other, our intuition didn't really work. So we went out to say, what is really determining the number of control nodes in the system? And the first guess we had, well, it's probably the hubs, because we know how important hubs are in different systems. So maybe here they're really important when it comes to the control nodes. So we said we took an heterogeneity network or a scale-free network. We grouped the nodes into three categories: the third that has the lowest degree, the medium third, and the top third. And then we said, let's see in each group what fraction of the nodes are known to be control nodes. And to our surprise, what we found is that the vast majority of the control nodes are really in the small degree region, and a very few fraction of the hubs, small fraction of the hubs are actually control nodes. So really, hubs don't play the control role in the system, and that's not only for model systems, but also in all these real data sets. If the hubs would be control nodes, then the data points for this real network should be above the diagonal. The fact that they're all under diagonal indicates that really the hubs don't play a control node in these real systems either. So that was the first surprise. So clearly hubs don't play that major role, and the reason is that hubs typically have many incoming links, so chances are that some other nodes already controls them, and you don't need to control it individually, and you know, so you can get the system controlled without them. But the real surprise came in the next slide. We said, let's go ahead and take a network, whatever that would be, like a regulatory network, and randomize it. That is, wire it completely randomly, but keep the same number of nodes and the same number of links. And for now, for this randomized network, let us calculate how many control nodes does it require compared to the original network. And we did that not only for regulatory networks, but for all the networks that we saw in the previous table. And we ended up with this particular situation. So this is the real number of control nodes, and this is the randomized version, the heterogeneity version of this network. And if the numbers would be the same, then it would be along the diagonal. The dots, the fact that they're scattered all over the place indicates that really there is no correlation between the two quantities, which is not surprising, because once you randomize the network, you're really changing its wiring diagram to random. And therefore, you don't expect that the control configurations will stay the same. So, fine. But then we said, let's do a randomization that is not completely random, in a sense that it preserves the degree of each node. So if a node in the original network had 3 outgoing links and 2 incoming, in every single randomized configuration, we'll maintain the 3 outgoing and 2 incoming links. And so this is what we call degree-preserving randomization. And let's see what would be the number of control nodes in these degree-preserved networks. And to our big surprise, it was the same as the original network. So why was this surprising? Because we completely randomized the wiring diagram while keeping each node's degree the same, and yet in this randomized wiring diagram, you needed the same number of control nodes as in the original one, which really told us that the quantity that is determining the number of control nodes in the system is the degree distribution of the system. Now, who is the control node is determined by the particular wiring diagram, but how many you need is determined only by the degree distribution of the system. And once we had that really we could apply a tool coming from spin glasses that to analytically calculate the number of control nodes in the system. And we were able to derive a number of quantities. So for example, we showed that we asked, how does it depend on the average degree, the number of control nodes? That is, if the network is denser, will it be easier or harder to control? And the answer is that there's an exponential dependence on the average degree. It's e to the minus average degree over 2. which means that the denser the network, the easier to control, the fewer control nodes you need. And that kind of makes lots of sense. If there are lots of links in the network, there are many means to control, to reach the other nodes from the control nodes, and therefore the control becomes possible. But it's a very rapid drop because it's exponential. So if you're making your network denser and denser, technically it becomes easier and easier to control. We also said, well, what is the role of the hubs? Not as much of the hubs, but the degree heterogeneity, whether all nodes have the same degree like in a square lattice, or there are hubs and many small nodes. And that's captured by the Gini coefficient, which just tells me if this age is very, very small, the network is very homogeneous. All nodes have the same degree. If this age reaches 2, then it means that there's a huge heterogeneity, that a few major hubs hold together many, many tiny nodes. And it turns out that the more heterogeneous the network is, the more actually control nodes you need. So if you put the pieces together, what we find as a trend is that the mean degree and degree heterogeneity are the two main factors that determine the number of control nodes in the system. And what this really means is that sparse and heterogeneous networks are the hardest to control, and dense and homogeneous networks are the easiest one. And the reason why this is really surprising to us is because sparse and heterogeneous ones, those are the hardest to control, are the type of network we see in most complex systems, from the cell to the internet and so on. So it seems that actually the type of systems nature and science and technology develops, really goes to the networks that are harder to control. They are sparse typically, and they're very heterogeneous. So what I would like to do in the last few slides, as I'm concluding my talk, is to show you kind of pull network science and the controllability together and see how would this apply to a system that we all to a certain degree are familiar with because we're part of it, which is like social networks and organizational networks. And what you see here is actually the employees of an organization in Hungary. This particular organization has, it's a company who has three manufacturing sites, one in Budapest, and those are the purple people, and 2 are outside of Budapest, one close to Budapest and one quite far away. Not so far actually, but relatively in their Hungarian standards is far away. And the question was, in this particular case, this was the real problem that the CEO of the company came to a small company in Hungary. His name is Maven 7. They're a social network company. And they asked them, help us to understand what is going on. Because every time the higher management and the CEO takes a decision, it's a completely different set of messages are getting to the workers. So there is a complete disconnect between the higher management and the rank and file. So they wanted to figure out how could they understand what is the source of the problem, how could they change that. So what Maven 7 has done is that they actually went in and they did an online interview of every single employee, simply asking them a couple of questions that are really pertaining to the organizational structure of the system. They asked them, whom do you ask for, whom do you turn to when it comes to advice about what's happening in the company, what is the latest news, what are the reorganizations and so on. So that is whom do you trust and whom do you ask information for in company matters. They had a number of questions along these lines which led them infer them really where is the information spreading from whom to whom. And the result of that investigation was a map like that. So, and now of course the individuals correspond to the size of the node corresponds to how many people nominated that particular person as being the source of the information about organizational matters. And this is interesting. You can see the basic features of many scale-free networks. There are many, many small nodes and a few major hubs. The network is too small to really claim it's scale-free, but the heterogeneity is clearly there. So that's not the point of scale-freeness, is the heterogeneity. There are few influential individuals and many not so influential. Now, the biggest problem in this map is if you look who are the influential people. So what I'm going to show here is that where is the higher management? These are the red nodes. This is where the CEO and the higher management are, and you can kind of see they are not hubs. The next level, the top managers, are the blue, and you can hardly see any blue node over there actually in the big nodes. And these are the purple are the ordinary managers. So there's one guy actually who's influential among those guys. And these were actually the lower rank managers. And what you see is that, the biggest hubs really come from the lower level management and what they call associates, which is a nice way to say workers. So of course, you start looking at it and said, who are the hubs? And in this particular case, we know who the hub is and who is the biggest hub and the most influential person. And that turns out to be the health and safety manager of the company. Now, the health and safety manager is a person who is actually kind of, it's not really a manager, it's an ordinary worker, but he's in charge of the health and safety. He has this title, though. And he's the only person in the company whose job is to go from location to talk to everybody in the company. What distinguishing him is that he knows everybody in the company because that's what he has to do, but he has no links to higher management whatsoever. So he's the source of the gossip, essentially, with the company. You know, whatever reaches him doesn't stay with him, and really the news are traveling within the company, never reaching the higher management, never going back and forth. So now, of course, the question is, what do you do? Should you fire that guy? Well, that's not really his problem. It's the higher management's problem who really created the structural hole that this guy is really filling in. So this is one example of how the tools of network science can just simply having the map is so instructive to understand the structure of the organization. So for example, this Maven 7 company who did this particular study, they by now mapped out about 250 different companies from anywhere from a few dozen to about 30,000 employees. And each of the cases, there is a surprise element like that. They really learn how the company works, go beyond the organizational structure that is the official one, and shows you where the real communication is in the system. What we did recently is that also to apply the tools of control theory to that and simply ask who are the control nodes. So, and this is what I'm showing here is not the control nodes. So the flickering ones are those who are not control nodes in the system. And the reason I'm making them flicker is that so we understand that the vast majority of the nodes don't qualify as control nodes. Because once I'm going to put the control nodes, they seem to be a lot, but really many of the small nodes are hidden under this really almost invisible category. So really, if you want to control this organization from a control perspective, all these flickering nodes don't matter in a sense because they're not really influential within the organization. The influential ones are actually shown in this slide, the red guys. And so what this does essentially gives you a picture of saying where really the information lies, where it is actually being collected. If you were to try to influence this organization, to change that, to move it in the same direction where you want to go as a leader, what are the points where you can actually intervene and make a change possible? So this is kind of showing of where you can take these tools and how you can write it. And of course, I would be lying if we say we really understand the role of these control nodes. We don't. This is a very new line of research, and we're kind of struggling to find data sets where we could correlate the control status with many other characteristics. But down the line, it looks like a very promising approach to try to think about both organizations and biological systems and many other areas. So stepping back, let's look at the big picture. So we talked about, earlier in this morning about the role of complexity and so on. And this is a slide that occasionally I show about how the different takes on complexity really kind of come up and, compare to each other in a way or the other. What you're going to see is that on the horizontal year, you see the horizontal axis, you see the years. And the vertical axis, you see the number of citations. Some of the most influential papers in complexity research actually have gathered per year. So it's not a cumulative, but per year's number of citations. So let me illustrate that. So for example, one of the earliest influential papers on complex systems is Lawrence's 1963 paper about butterfly effect, which for a decade nobody cited it at all. And then about 10 years later, it was kind of discovered and rediscovered, and that was the same time when chaos came along, randomization group, Wilson's paper, this is Wilson's paper, came along, and Feigenbaum's paper came along, and really the whole concept of chaos and nonlinear dynamics have exploded. And as a result, the number of citations have gone from 0 to about 100 and eventually 200 per year. So this was kind of 1970s, 1980s. It was about chaos and nonlinear dynamics. Then came kind of early 1980s and came fractals. So what you see is Mandelbrot's book about fractal phenomena, Hopfield paper about neural networks, then the self-organized criticality. These are papers we're all familiar with in this community who have really shaped the way we think about complex systems. And this was kind of the situation. They've really been truly influential until the late 1990s. And the end of 1990s, kind of network science started to emerge. And so here I'm showing 4 papers about that, and you can see how we actually look like. So, which makes you wonder what is going on. what has happened that really in complexity that has really allowed some of these papers, because this is not my merit or Duncan Watts' merit, it's the community who's really made it possible. And one way to think about it is that, yes, the thinking about complex systems have really come of age. But the other way of thinking about it is that really network science have offered the language through which really many different disciplines have adopted as their own and have fully associated with it. You know, one could argue, and I've been part of both the chaos field. My first paper was in chaos. My subsequent many papers were in fractals, is that despite the excitement we physicists felt about it, it was really staying within the physics community with a very few exceptions that went out of that. And network science is probably the first area in complex systems that have truly transcended physics. If you think about it, graph theorists and mathematicians will tell you this is all us. You know, it's Euler invented it in 1730, and since then, you know, we've been doing that. If you think about computer science, this can come along and say, well, this is us. It's the internet and the World Wide Web, and it's our field. Biologists have invested hundreds of millions of dollars in the last 10 years to map out biological networks. Neuroscientists now already got invested in mapping out the brain. Sociologists will tell you, what are you talking about, the new field of science, network science, because since 1930s we've been looking at social networks. And they're all right. And what actually means is that really this has been the area that has been truly adopted by many fields of saying, this is not just only a fad, but this is part of what we do on a daily basis and essential for us to understand networks. And this is a question that a number of actually official bodies have dealt with. The national academies have put out 2 different reports on network science, trying to define what the field is and how you deal with that. And the definition that came up is that really it's an attempt to understand networks emerging in nature, technology, and society using a unified set of tools and principles. And I think that's really important because what is really new here is the discovery. It's not that skillfulness, it's not the small world effect, it's not whatever property you want to talk about, but the discovery that despite the apparent differences between different networks, many networks emerge and evolve driven by the same mechanisms. Once you develop the language to talk about one network, you have the language to talk about other networks. It could have been otherwise. It could have been easily that the World Wide Web will be fundamentally different the way it looks like architecturally from the cell, for example. And then we would not have a field of network science because there would be nothing to talk about among different disciplines. But the reality is that it turned out that networks have provided this language that is not, networks are not the ultimate answer to complexity. Complex systems have this other layer, which is the dynamics, which is what I tried to address in the control part. But I could go as far as to say, we will never understand complex systems unless we really understand in quantitative terms the networks behind that. So the previous slide, what you show, is a reflection of that, of many communities coming along and making the real effort to understand these networks behind these complex systems. Thank you very much for your attention.
So, fantastic talk. I know you've had your hand up the whole way through the talk, so I will come to you first.
I'm sorry, I didn't notice your hand, so.
I didn't either, somebody else did.
All right, perfect.
We have about 30 minutes, so lots of time for questions.
You talked about modeling networks from more like an abstract graph network point of view. Mm-hmm. Initially, when you talk about controlling networks, you talk about dynamical systems, particularly linear dynamical systems, but complex systems are non-linear dynamical systems.
Yes.
So I'm wondering if it's possible to have a mixed level model of complex systems whereby you capture the not so important aspects of the network with a higher level network of model, and then the important dynamics of the network with like a nonlinear dynamical systems, and then you use nonlinear model auto reduction to reduce the size of the matrix of the differential equations or whatever to make it faster to simulate or analyze. Is it possible to do that? Can
I be a bit more ambitious on that? I would like us to be able to address head-on the full nonlinear problem. I mean, that's eventually the goal. I spoke today, for example, let's take the control aspect. So I spoke only about the linear aspect, partly because much of the control theory, the simple concepts have been developed for the linear networks. But you can do nonlinear control as well. And actually, my co-author Jean-Jacques Slotin's work, who actually has worked with us on this control problem, he has written actually the basic textbook on nonlinear control. So there's a whole theory developed on nonlinear control, and the only reason we actually apply this one to linear systems here is because it was more like a proof of principle that how you go from the network to this criteria, and we fully intend to go in that nonlinear direction. It's not easy to do, but there's one caveat that I'm not expert on, but Jean-Jacques is always telling me that I should pay attention. His claim is, as a control theorist, is that nonlinear systems are easier to control than linear systems. Because often nonlinearities give you lots of decaying modes that you don't have to control the system, and it makes it somewhat easier to do so. So therefore, when you actually try to control the system, you have an easier way of doing so than in the linear system. But the drawback of the nonlinear systems is that each system has to be taken on its face value. You can't just simply write a matrix equation up and get it. But on the other hand, and that's the last caveat I want to add there, is that if you want to understand the controllability of a nonlinear system, you still need to check in every single point of the phase space whether the linearized version is controllable. So in that sense, what I presented here is the kind of the first step towards addressing the nonlinear system, and then of course you have to add. So, but to conclude it, I'm not shutting down the possibility that we all want, and maybe you will be the one who develops the full theory of nonlinear control, but I don't think we need to stop there, and I don't think we will stop at the linear systems. It's just a step in the road. Szívesen.
Hi, I'm Robinson from Australian National University. First of all, I just want to ask you about what sort of visualization software you used. Really nice. And second, just was wondering out of curiosity, because you're addressing control theory ultimately to address problems in dynamics. I think it's evident that, classically, Laplacian of those adjacency matrix networks, they play central roles in those dynamics. And just wondering, did you find any sort of relevance of these control nodes to the Laplacian spectrum?
Sure. So regarding the software, we don't have a favorite software. For each problem, we develop a different kind of, at least the rule in my group is that we don't use ready-made softwares. We just kind of, everybody develops their own whole thing. But you mean the visualizations, what we did? I guess everybody just does it on their own within the lab. The second question was, again, the main question was regarding whether we can validate the control nodes. And I think that was my understanding, is that how do we know whether they're important? And as I tried to say towards the end, we don't right now. And that's one of the big areas actually of research now in my lab, is that we're looking at lots of different systems where we have lots of other node characteristics to try to correlate the control configurations. In order to do that, you need to go a step beyond what I presented here. One of the things that may have escaped your attention is the fact that there are many control configurations. So you may be part of a control configuration in one configuration, and in the other one, I don't need to control you to control the system. But it turns out, and that's what we're able to prove, is that there are some nodes who are always controllers, and there are some nodes who are never controllers. And then it turns out to be a difficult problem to characterize the nodes who are sometimes a controller, but now we've worked with Laszlo and his students to work out a sampling algorithm by which we can assign to each node a number to say, you're always controller, you're never a controller, or between 0 and 1 saying what fraction of the configurations you are a controller. And that tool, actually, that we're just writing up, will be necessary for us to really go to the next step and try to look at what is the meaning of these nodes. Because now if you just take one control configurations and try to validate one particular node with a controller, may not give you the full picture, because may not actually be a controller in the real world. So, but this is the biggest challenge for us, and we're kind of busy working on that. But chances are that the answer will not come from us, but from somebody else.
Hi, I'm a student from NTU. So I want to ask about matching. So you said that when you do maximum matching on a graph, and you have different control configurations. So what are the commonality between the control nodes? Do they have any features in common that they become control nodes. How is it related to the matching outcomes of the algorithm?
Mm-hmm. Well, I mean, this illustrates very well. So, so if you look at it in all of these configurations, this was always a control node, and this was always a control node, and these were the guys actually who could change back and forth. So it turns out is your topological position determines whether you are in one or the other category. So a simple-minded answer that is easy to prove is that if a node has only outgoing degrees, it has to be always a control node because there's no way other way you can control it. But there are some much subtle cases as well of how you achieve that. So in a way or the other, I mean, you can reduce it to the simple topological characteristics for the extreme cases, the always control and the never control, but the in-between, there is no simple rule that you could just simply say, if that has that characteristic, it's going to be sometimes and not always a controller. But we have the algorithm to do that very efficiently now. So I think we'll be out probably in a month or so. We'll publish that, and that will make it easy. And then from there on, whether it is or not relevant, it depends on what good data sets you have to correlate it with. Mm-hmm. It's not on.
I'm thinking of these networks in a particular context. Okay? Let me think of an example. Think of the global crisis. Right? It emerged in the US, a small part of the US. Now, when I think of, say, the connections in the global economy, let's think of two types of connections. Countries are connected through trade. They're connected through financial connections, through banks, and so on and so forth. It can make the network, or the functioning of the network, dependent upon where the shock arises. So I'm trying to combine what we heard in the morning with what I'm hearing now.
Yeah.
Because the way contagion will manifest itself in the time dimension will depend upon where the shock comes from and what the nature of the shock is.
Yeah.
And I'm trying to think of the networks that you've established. Here, a link is a link. I'm trying to think of what you just mentioned, that sometimes this link works, sometimes it doesn't, or the strength of the link may be different depending upon the nature of the shock. Maybe I'm not very clear.
No, I think I know where you're heading, and there has been quite a bit of work in that direction in the context of what we call cascading failures on networks. So the idea is that you have some quantity that is flowing on the network, like electricity in the power grid or money in the financial network, and then you knock a node down. When you knock a node down, that will have to redistribute the resources to the remaining nodes because current cannot be preserved. You have to send it around, or money will start flowing in other directions, and so on. And that will make the other nodes tip as well because they may not have the capacity to handle the extra load. And there's quite a bit of work in this direction. And when you say, let me try by knocking out each node individually and see what is the size of the cascade you get, you typically get a rather universal distribution of an exponent 3/2. So the cascade size distribution will be a power law. That has been shown in a wide range of models. So we know it's pretty much model independent, and it's really easy to understand. So what this tells me is exactly what you're saying. It depends where you start from. In some places you start a huge avalanche. In some places you start and you do not much. You do a local breakdown, and that's the vast majority of situations. You have many small banks failing, many small companies, and so on. But then occasionally you hit it in the right point, and then we'll start a major avalanche across the whole system. So conceptually, the system is well understood. Would we be able to make sure that we don't have another crisis next? The limitation is really the lack of maps. Even before the crisis, I had one particular friend of mine, Imre Kondor from Budapest, and he's been going around, and we thought he's nuts actually, because he kept going around and said, these banks have so much owing to each other, and that's not a public information, that we really need to understand it. And they did even small simulations on the Hungarian market to see how these cascading failures will work out. And I really thought that, oh, he's just being alarmist about the whole thing. And this was about 3 or 4 years before the thing happened. And actually, I was talking with the other night, that was actually with some of the people here, who was talking with Stiglitz, and the question was, could you ever map these things out? And it turns out that even the current regulation in US doesn't go far enough to get these maps. So now it's forcing the banks and the companies to disclose lots of dependencies they have among each other, but they just have to disclose it towards one particular government agency, so you can get access to it for research purposes. So if the government agency doesn't do its work, and even the government agency has to really do lots of work to get that information from them, so it's not automatic. So at the end of the day, in order to address this in a quantitative manner, you would really need to develop a systematic way of having the maps in an up-to-date fashion. And I think there is enough knowledge of this system that you would know what kind of maps you would need and what kind of dependencies you would need to actually start simulating these systems. But I don't think that this thinking has really penetrated high enough in the government and regulatory agencies to really start acquiring this type of data sets.
So I'll just comment on, I assume you're referring to the Office of Financial Research, who's been kind of tasked with gathering this information of kind of who's trading with whom among the banks. So I'll just allay your fears. They are aware of kind of the value of understanding the networks and really trying to analyze that.
You mean you assume that this information should exist? I mean, at the same time, lots of these companies have lots of reasons to not to make it private.
No, they're tasked with gathering this information. But of course, it's a new agency that's just been created with no head who's actually been approved by the Senate, et cetera.
So that was the one that I had a discussion with Stiglitz, and he told me that he doesn't have that agency doesn't have enough power to gather the type of data you would need for that.
I see.
So it goes in step in that direction, but not far enough.
Right. It's definitely there, but I just want to say, but I know they are interested in sort of networks and trying to use that information, et cetera, et cetera. So it's not going to be just pure sort of economic, general economics analysis.
Well, the way I think about the reason hasn't really gone too deep into this area is actually even many years ago, when I tried to kind of see what is going to be the future of network thinking, I said, biologists will pick it up very fast because they're very fast, they are really mobile when it comes to developing new technologies to measure the maps out. And I always thought economic systems and financial systems will be one of the slowest one because the community has such an inertia in many ways. And that's what we see. Now, there are a couple of really interesting works both in the financial and in the economics literature about the role of the networks. But they're really fascinating from economic perspective. From our perspective in network science, they're really primitive because all they do is, let me take 6 nodes and show there is a network effect. Geez, how interesting it is. Now, it is interesting because it's a major step from the economics perspective in venturing in an idea in the direction that hasn't been really ventured before, but it's still a far cry away from the type of complexity that we see in the real markets or in the financial systems. So they're moving in that direction, but with the time scales that is characteristic to that particular community. We'll get there. How long will it take? Well, maybe a few more crises before that.
Yeah. In one slide, you show that if we change the network topology, but we do not really change the node degree distribution, we will actually have largely the same number of control nodes if we do try to optimize that part. So my question is, like, when we make such kind of changes, I understand that the number of control nodes remains largely unchanged, but are we ending up with the same side of node, or like, so the number does not change, but we are having another side of nodes as serving as a control node?
So the identity, so let me walk again through that process. So we do what we call a degree-preserving randomization, which each node in every random configuration will the same number of links incoming and outgoing. But to whom it connects will be different. The number of control nodes remains unchanged, but the identity changes. So, and that there is no way of saying that, I mean, there are still certain things that will probably be true in a sense that if a node had only outgoing degrees, will always be a control node because that hasn't changed in the randomization. If you had only outgoings, you're going to still have only outgoings. But anything else, the never control and the sometimes control the nodes, they will always change their identity depending on what configurations you end up with because the wiring diagram has changed. Who is controlling you has changed fundamentally. So in that respect, I think it's interesting from the way of characterizing the whole system, but you're getting really little insight to that randomization about the individual nodes. You are just getting insight about the global or control problem. Mm-hmm.
So I have a question about the relationship of network science and how often it's being cited compared to other fields, Mandelbrot and his sort of rise and fall, and all of this, and how much this relates to software and the availability to do these kinds of analyses and projects. If you think about social sciences and how often statistics papers are cited, that's also risen in a similar kind of fashion because of the rise of the personal computer and people's availability to do the statistical analysis, right?
Yes.
So there aren't not that many computers that could do network analysis in the early 80s that people had, and now, of course, we all carry them in our pocket.
Okay.
So has there been a control study with how much of that is involved?
No, actually, I would go further than you. I think the reason why at the end of 1990s network science have really emerged in such a full force and so rapidly has grown is not because a couple of geniuses came along and said, voila, here are networks, but because the data became available. And it's really a byproduct of the internet allowing us to collect large data sets and study it. And once we studied it, if you would have been in my place, you would have probably the same things as I did. So we were lucky being at the right place at the right time and having the right intuition to look at these large networks because those properties were there. They were kick your eyes out, essentially. They were so obvious. It's just that we were the first one to have a chance to look at in a systematic manner at these networks. So it's really the data. So when you say statistical papers are becoming more cited, well, because indeed we have more and more data and we need statistical tools. The network science papers are getting such an amazing number of citations is because these early papers have provided some concepts that are generally applied to a wide range of networks, but the number of networks that can be applied, the number of data sets is really increasing almost exponentially. And at the end of the day, whether you are biologists, sociologists, or organizational researchers, you look at your network and you need to analyze it and you need to go back to these early tools that were developed back then. So that's really what has changed, however, in the last 10 years is very honestly, in the positive sense. I mean, 10 years ago, like 98, there was no language how we could talk about networks. If I just gave you a network, you know where to start. What would you measure? How would you analyze it? How would you talk about it? What is important and what is not? That has changed drastically. So if you were simply come up with another network for whatever is interesting for you with 10 million nodes or something, we have a whole battery of tools that you can apply, and within a few hours, you know the basic properties, you know what you should pay off, what is usual, what is unusual, where you should start looking at the science of it. So, and I think that's an important change, but that increase is really a reflection of the data availability and the need to analyze these data sets, and some of these early papers have provided some of the insights to how to get started.
If you look at any engineering applications like network of embedded systems, like Internet of Things, like you have millions of or billions of wireless embedded devices connected to each other, or network on chips where you have circuits that can link thousands of cores on one processor.
No, we never did that. I mean, partly because we just don't have access to data set like that. And then also, most important probably, in order to properly analyze those systems, you don't only need the data set, but you need to understand those data sets. And you probably have to bring in some domain experts and say how you correlate that. So, I mean, that's the way we want to pursue with some of this control stuff, is to get some of the data sets that are well understood from a control perspective, apply these tools, and really start to understand the role of the control nodes and the many configurations and so on, and how you actually make sense of all of that.
If there are two networks that are combined, can you make prediction which one will be more dominant? Or is it safe to imagine what will happen if one network try to invade another network? Is it safe to imagine that if the nodes will attack the control nodes, that network will have a bigger or a better chance of invading that network? Because this is very important for biological systems
Sure.
in drug discovery, etc.
Yes, I mean, we actually been involved in looking at how viruses attack, human cells, and we have a paper coming out very soon, hopefully, on that. I don't think there's a generic answer. So for example, in the case of, we looked at EBV and HPV, which are two cancer-causing viruses, and how they attack the human cell. And there are a number of things you can draw. The biggest conclusion was that the diseases that the virus is causing can be explained by the vicinity of the nodes that are being attacked by the virus. That is that, if a certain node, the certain viral node actually interacts with a certain protein of the human cell, and that protein is involved in disease X, then very high chances are that the consequence of the virus is that you develop disease X, whatever the symptoms of that are. So in that respect, network aspects are very useful and very informative. Network thinking is very informative. I think that will be the future to really understand how a virus invades a certain cell. But there is no generic theory of how one network attacks the other one. I mean, we have looked at two examples. There was a recent Nature paper by one of my former postdocs on kind of HIV infection and so on. We have too few case studies to really draw a generic conclusion on that.
Maybe just a short follow-up
Sure.
question. How self-similar are if you look at the control networks, the nodes that form the control network, how self-similar is this to the bigger network, which is composed of all the other networks?
I don't know, to be honest. We never kind of looked in that sense. First of all, self-similarity has a very precise meaning in other systems. And while some of these networks are fractals, others are not. And we have not really even crossed our mind to connect the two concepts together. So I just don't know the answer.
So I think it's about time for the break anyway. So I'd like to present Laszlo with a small token of appreciation for agreeing to give a talk. So thank you.
Thanks,